and honor today to have Professor Makoto Ikeda with us. So Professor Ikeda received the BE, ME and Ph.D. degrees in electrical engineering from the University of Tokyo, Japan in 1991, 1993 and 1996 respectively. He joined the University of Tokyo as a research associate in 1996. He is currently the director and a professor with the Systems Design Laboratory D-Lab, Graduate School of Engineering, University of Tokyo. He has been involved in various activities to promote VLSI design education and research in Japanese academia since 1996. He has led the AI chip design project for Japanese startups, supported by the Ministry of Economy, Trade and Industry of Japan since 2018. His research interests include hardware security, smart image sensors for 3D range finding, and time domain circuits, including asynchronous controlling and associate memories. Professor Ikeda is a senior member of IEEE, senior member of the IEICE, and a member of ACM and the Information Processing Society of Japan. He has been serving as a distinguished lecturer for the IEEE Solid State Circuit Society, and we had one of his lectures online in December, and we are very happy to have him in person now. And he has held numerous positions at international conferences, including the International Solid State Circuits Conference, ISSCC Technical Program Committee Chair in 2021, Program Chair of the Symposium on VLSI Circuits in 2017, and the TPC Chair of the Asian Solid State Circuits Conference in 2015. Thank you, Professor Ikeda, for visiting us, and we look forward to hearing your presentation.
Thank you very much for kind introduction, and thank you very much for coordinating my talk again. Because the last December, I was expected to come here, but unfortunately that was the holiday season, so I delivered my talk online. But definitely I really want to come here. So this time I have a chance to come to India, so I extended my stay to visit here. So anyway, thank you very much, and I really happy to deliver my talk. A bit different from the December one, but basically I'm working for the hardware security or accelerator design for crypto algorithms. But today I also adding a bit different topic as well, named the chip design and fabrication democratization activities we have been doing for past 4 years. So let me start. So by the way, most of the hardware security portion have been supported by the government, mainly coming from the Ministry of Economy. And so I really appreciate their funding support. And in addition to that, the so-called Agile-X project, which is the chip design fabrication democratizing activity, is supported by Ministry of Education. So this is the outline of my talk. So I'll talk very briefly about the functionality in crypto algorithm. And then I'll talk about the sort of mathematical background up to the hardware implementation for the basics. And then using attribute-based encryption as an example for the functionality of the crypto algorithm. And showing the design example on FPGA and how we extended that to the ASICs. And the last portion, I will talk about the work we have been doing for Agile-X project. So maybe you're mostly working for hardware security. So you may know the functionality. Of course, the internal functionality should be sort of the fully homomorphism. But before that, we have a bunch of the functionality available with like the attribute base, that we don't need to have the explicit key to encrypt or decrypt or the digital signature authentications. Of course, the other functionality that could be very useful is searchable encryption. So that searching operation can be done in cyberspace instead of decrypting the data or decrypting a tag to searching operation. But that is very helpful if you want to extract the statistic in the secret data. For example, if you have a secret data like a card in the hospitals, but if you want to extract the how many cases of, I don't know, COVID or any other the virus affected people, if you are a doctor who has authority to access to the data, that's fine. But no other people can access to that from the outside because of the personal privacy issues. But if we can extract freely from outside using this kind of searchable encryption, it could be very helpful for the extracting the statistics without getting help from medical doctor or something. So there are other many kinds of the functionality existing, but the problem here is most of them requires a huge amount of computational complexity. So although people assume that this kind of functionality might be helpful, still in reality, people resign using that because of too much they're slow or something. So that is the reason that if we can accelerate this kind of operation by hardware, that could be very helpful, or that could be realize this kind of very useful functionality in reality. So that's the major reason that we have been coping with the functionality. So I already touched a bit about attribute-based encryption, but the attribute-based encryption enables you to do encrypting data or decrypting data or whatever without having the explicit key. Instead, using the attribute-based attribute, like you have been as an engineer for more than 7 years, then you are granted. Or if you are in a research division, you are not granted, or so on and so forth. So with this process, once you are granted, then key will be internally generated. Then the encryption or decryption or any other operation is done internally instead of explicitly exporting the keys. So that helps reducing the revealing the key to the outside to the revealing entire secret data. Of course, as I mentioned, the homomorphism is one of the eternal target for functionality. So many of you are seeking that direction as well. So realizing additive or multiplicative or fully homomorphism, that you can realize any mathematical operation as well as logical operations in cyberspace. So this is very useful, and sometimes I receive questions that why you are using this kind of functionality instead of just doing the fully homomorphic encryptions. This kind of generalized the homomorphism very useful, but you have to think of how much computational complexity you need to implement. At the same time, how much memory you require. That is very serious issue. So, of course, those are the stuff that you cannot realize by this kind of functionality. That is the time you employ fully homomorphic encryption. But if you have any other chance to implement this kind of functionality, then sometimes instead of using fully homomorphism, utilizing the functionality only will be helpful. So that's the reason I have been still working for functionality. Of course, partially I'm also working for fully homomorphism, but that's a major reason. And so basically, most of the functionality these days basically based on the elliptic based encryption. Of course, right now people are seeking the functionality over lattice-based encryption. Of course, in addition to the fully homomorphic encryption. So situation might be a bit changing, but still, at this moment, most of the functionality is realized based on the elliptic curve. So elliptic curve, of course, most of you are familiar with that. It is defined by the geometrical operation over the elliptic curve. And so it is very easy, and the target should be the calculating k is the integer, times p is a point, geometrical point over the elliptic curve. And then you will find the q that is on the elliptic curve. From the q, finding the k is a very difficult problem, which is called the discrete logarithm problem over elliptic curve. And that is a source of security of the elliptic curve. At the same time, this is not the real value defined over the real value, but over this kind of discrete or the value over the Galois field. So this is very discrete number. So that's the reason we need to have this special computation named the modulus operations. Then how you can realize the functionality? So for doing that, we need to have so-called higher extended field operations. It is something like the from the real number to complex number, adding the imaginarity, which is another dimensions. So just the same as that, for the case of the extended field, we use 12th extended field. That means from the one-dimensional number to 12th dimension number system. So that means if the number is in 300 bit the space, the extended field's number is something like almost 4,000 bit of the number space. So you can somehow imagine, recognize how much data you need to cope with. But anyway, this is the still the mathematics over the elliptic curve. So the fundamental operation is just the same, but still we need to cope with that. Then to realize the functionality, of course, the basic standard operation is required. Of course, some of the functionality like hash function is requiring, but at the same time, we need to have the elliptic curve-based operation over the extended field. And at the end, we require the pairing operation, which are realizing bilinearity mapping. So that is the mathematics we require to realize functionality. So before going directly to the implementing their functionality, let's look at the individual, the hardware acceleration for individual mathematics. So for elliptic curve-based acceleration, if we relatively simple, so we want to realize this kind of k times g, as I mentioned, which should be most of the mathematics. But to realize that, if you directly solve the equation, you will obtain this kind of the addition, subtraction, multiplication, and divisions. And these operations are so-called the modulus operation. So addition and subtraction and multiplication should be okay, but the division takes quite a long time. So avoiding the division as much as possible will be the best, most important portion. To do that, we need to transform the coordinate from the ordinary rectangular affine coordinate to this kind of projective or Jacobian, or sometimes if we don't need to require y-axis, we can use x coordinate. This is mathematics, yet. And then we have the engineering part existing, like the how many data path word size we can implement, or how many pipeline stages we can put, how many processing elements we can realize, and so on and so forth. So we have explored some portion of that. Of course, it's not so easy to explore exhaustively, but we explored how many pipeline stages for modular the multiplication required is the optimum. But at the same time, we need to do this kind of the scheduling, that how many clock cycles required for this kind of operations. So these kind of sets of the optimization is very essential for design optimization. But before they come to the optimum, we need to see the unique character of the equations, and also for the security. So this is the set of equations to calculate the one, say, this kind of operations. So if you are the software programmers, definitely you will use this one. But assuming the four-stage pipeline, the situation is drastically changing, because this having the very strong data dependency among each computational steps. So instead, this one having the relatively better or the same number of clock cycles at the end. So maybe you might choose either of these two cases. But the problem is, I haven't touched anything about the side channel in this talk, but if you're keen about side channels, timing attack is one of the very critical the attack techniques. And for this case, the storing or write back the data sometimes causes the timing difference. For example, I haven't mentioned detail, but for the case of ladder, the implementation, you need to choose either the result of addition or doubling at the end. So if the completion timing are different, this causes sort of the timing, the leakage to the outside. Unfortunately, these two cannot be solved, because this having the processing element, the dependencies, so we cannot move this one until the end. This is the same. On the other side, for this case, fortunately, this having no conflict of the timing slot after this timing. So we can shift one clock cycle toward the end. Then we can uniform the completion time that prevent the timing the leakage. So coping with these issues, although this requires 2 clock cycles longer than the others, we need to definitely choose this one for the sake of preventing the side channels. So this is what we need to do during the design phase. Of course, we need to think many other stuff, even coping with the side channels. Then how about the data path, the word size? For this case, we employed 256-bit key, and we explored the 256-bit data size, word size, down to 128, 64, and so on and so forth, down to 8-bit. And this is the gate size or areas, and this is the required time for the ECDSA operations. So of course, this is obvious that if you use the 256 or full word implementation, it's very large but very fast. But if you go down to at some point, area will be saturated. This is because we implemented the internal storage as using crypto instead of using the SRAM for the sake of access time. So anyway, even data path is 8-bit, we need to utilize 256-bit the storage for the intermediate data as well as the parameters and so on and so forth. So that limit the area shrinkage, even you decrease the data path word size. So clearly there should be the optimum existing. Of course, if you utilize SRAM for the data storage, you have the access, the time, the overhead, but still the total amount of area will be drastically decreased for some the optimum cases. So this is what we observed, and we fabricated the extreme case of this very high performance with huge gate down to a very small one with SRAMs. Measurement results shows that this is very high performance with 30 microsecond operation, but with almost 1 watt operations. For this case, this is relatively slow, something like 100 millisecond operation or above, with only 3 milliwatt operation. Or if you decrease the power supply voltage down to lower, then it becomes almost 100 microwatt power consumption. One of the interesting feature here is that if you decrease the power supply voltage down to the so-called energy minimum point, this consumes only 3 microjoule per operation. On the other side, this one consumes still 100 microjoule per operation. So this might be a bit contradicting with the power consumption, but this is obvious that this takes quite a long time if you slower the operation, and because of the leakage, this becomes not energy efficient. On the other side, for this case, this the most of the gate inside is operating all the time, and also the computational time, even in the lower operating voltage, is relatively faster. So because of that, the leakage component can be I shouldn't say negligible, but very small comparing with this case. So because of that, this result in the much higher energy efficiency than this one. So if you are thinking of the operating on battery operation, this might be the solution instead of using these low power implementations. This is what we learned, and what we are surprised. So anyway, using this kind of design space of exploration, now we can have the very high performance one with the very power hungry, but the very low energy consumption, energy minimum point, or very small but very low power implementations, and anything in between could be possible depending on your requirement. So that is what we discovered through these researches. Then they're going to the pairing. So as I mentioned, pairing is something like 12 extended field operations, but basically the basics are just the same. So we can just expanding the equation down using the additional dimensions. So but the question is which the field we optimize the data path. So there could be a possibility expanding everything down to the primary field, or we can do that everything in 12th extended field. So either would not be suitable, and then some of the mixture basically based on the second extended field with some of the primary field the processing element would be the best optimal. So with that, we formed this kind of database with secondary extended field multiplier as the main entity of processing element, but at the same time we put some primary field multiplier and also some constant multipliers, so that to minimize the number of clock cycles. Of course, we intensively explored how many pipeline stages for this secondary extended field multipliers would be the best optimum, and for this case, we decided to utilize 12th at the stage fully pipeline multipliers as the functional unit. Of course, we have carried out intensive scheduling. At the end, we come to realize the very huge chip with 3 million gates. So as I expected, 3 million gate result in a very high performance pairing operation, about 30 microseconds, but with almost 3 watts. So this is again because the almost 80 to 90% of the transistors are in operation for all the times. So there are no dark silicon existing for the modern CPUs. So that's the reason the power consumption is so high, even only 3 million gates. On the other side, the performance-wise, before starting the hardware implementation, many the software people mentioned that the pairing operation requires at least 10 times more computational complexity or time than the elliptic curve-based operation. But at the end, because of the parallelism and so on and so forth, this resulted in almost the same performance of the elliptic curve. So that is the very important portion that the hardware can give you the opportunity to realize very high performance in operation if you can extract the parallelism and the out of the algorithms. Of course, but many people assume that the performance improvement by 100 times or more will be important to really realize the functionality in reality. So this is only 10 times improvement. So how we can do further? One possibility will be utilizing advanced process, because this is pure digital implementation. So if it could be very easy migrate to the advanced process if you have money. So this time, fortunately, we got some funding. So we tried 12 nano FinFET instead of 65 nano process. So a bit unfortunate thing was we haven't fully optimized in the physical implementation because the students are not so expert for such physical optimization. But still, even so, almost the same, because this is coming from the same RTL, so same number of gates. And performance-wise, it is something 3 times the higher performance than the 65 nano. Even we haven't utilized any, I think, PLL and so forth. Of course, power consumption is about 1 watt. So power consumption is reduced by factor of 3. Performance is improved by factor of 3. So power efficiency improved by factor of almost 10. So that is the power of the advanced process. So I'm really expecting that if we can utilize 2 nano Raptors the fab, maybe we can realize 10x more performance improvement or further. That is one thing for performance improvement. But at the same time, we can think of further parallelism in algorithm level. I just mentioned about pairing operation, but if you utilize functionality, the pairing in functionality, then even the pairing operation having the parallel or free from data dependencies. So we can put multiple pairing engines inside to accelerate the functionality. So for this case, we put the 3 cores as the pairing accelerator for the functional encryptions. And they just showing here as sort of macroscopic scheduling. The sort of searching operation or some other functionality can be easily parallelized just like this, instead of the sequence of pairing operations. So with this, we have demonstrated further the performance improvement using the multi-cores. Well, of course, if we utilize the advanced process, we can again obtain the performance improvement. So this is what we learned. At that time, at the beginning, we utilized the BN12 curve as the pairing curve, but after a while, many people mentioned that this is not so secure, and we need to hope to further secure curve like a VLS12 381 or something. So we are now seeking that direction as well, but before that, we implemented our chip connected to the PC, which is running the searchable encryptions. And even the coping with the PCI, the latency, the degradation, we demonstrated that the faster operation than the CPU. So this is the advantage of hardware acceleration. If we integrate this accelerator inside the CPU, then the performance improvement would be much higher. So, and of course, the power consumption wise, comparing the CPU operation, this consumes quite a low power. So this is the advantage utilizing hardware acceleration. And next topic is, as I mentioned, because elliptic curve we have standard, but pairing we don't have any standard existing. So with that, how we can choose the curve parameter will be very important aspect. Well, as I mentioned at the beginning, we utilize this BN254 as a curve parameter because that is coming from the company who is working for searchable encryption. And at the beginning, they mentioned this curve maintains 128-bit security. But soon after that, people mentioned that security will be degraded by 10 to 20 bits. So it is no more practical to utilize for secure applications. So because of that, we need to hope either BN512 or VLS 381 or any other curve parameters. Which curve parameter should be the best is quite unknown. Of course, if we have plenty of design power, we can do everything by scratch and comparing the performance, but it's not practical at all. So instead, we realize sort of the design automation for pairing hardware. Just feeding these curve parameters, we can automatically synthesize the design utilizing these design templates. This is something like a template-based design automation. Of course, this is not 100% optimal because if you recall the architecture in the past slide, we put some other functionality other than the second extended field multiplier. So that causes the performance degradation a little bit, but still this could give you the hint what will be the expected performance with this curve parameter. So of course, with this kind of intensive scheduling, for this case, you can see almost every the slot is occupied. That means the scheduling is almost perfect comparing this one. But anyway, so we demonstrated many curve parameters with this design, the template-based design automation, and some of them we have the handcrafted design, and we compare with the performance and the latency wise, it's something like a 2x degradation. This is coming from the additional functional unit that should be that is allocated in hand scratch design, which is not allocated in the design template. Of course, we can attach such kind of the functional unit in addition to the template, but if you look carefully into this kind of the curve parameter or equations, constant multiplier or other functional unit should be synthesized from this curve parameter, which is not automatically realized. So that because of that, it's not so easy to do everything in this design automation. So that's the reason we omitted that portion. But anyway, most of the cases, the power is something, the performance is something like 2x degradation. So with knowing that, we can somehow estimate what will be the expected performance, or what is the expected gate size, and so on and so forth from this design automation. So once we identify which parameter we are going to use, then we can obtain the optima from that template. Okay, then going to the main agenda, attribute-based encryption. So basically, because this is very complicated algorithm, so we implement it onto the FPGA at the beginning. So what's the difference between the data path of FPGA and ASIC? I think many of you are having experience using FPGA and also ASIC. So how do you think about that? So this is the one of the hints for that. So assuming if you have 384-bit data path or modular multipliers, and we can split the one side into this fraction, like 192, 96, and so on and so forth. What will happen? So according to that, number of clock cycles should be green one. I should say increase from the full world size down to the smaller world size. Of course, clock cycle clock frequency, I should say, decrease when we use the smaller the world size. Area also decrease. But then, depending on the metrics you are going to use, for this case, if using area delay product as the metrics, this matrix, I should say decreasing according to the size of the data path. What does that mean? For FPGA, basically, small the data path gives you the better performance. That is what we observe from this one. Of course, depending on the algorithm, it might be a bit different. On the other side, if you implement onto the ASIC, of course, the general trend is almost the same as FPGA, but increase or decrease is slightly different from the FPGA to the ASIC. Then you could see this kind of the drop for the case of full word size the implementation. So this is clear the idea. Using this full word data path will be the best optimum for ASIC. This is the part we usually explain, but we haven't examined like this. So that's the reason I showed this one. But this is very important characteristic. So I often ask that you are doing this job. Why you are using ASIC instead of using FPGA? FPGA is much easier for you, and but this shows a completely different idea. If you are using ASIC, this is the best optimum. If you are using FPGA, this is not the optimum. So optimum point is completely optimal architecture or solution data bus is completely different direction. So that is what we learn. So because as I mentioned, for the complicated algorithm implementation, we need to fully depend on the FPGA. So for that, for the data path, we need to optima for the FPGA. So of course there are many the algorithms existing like Karatsuba or Chinese reminder theorem and so on and so forth. In addition, we use sort of lookup table-based modular multiplier as a basis of the operations. Well, I skipped the detail, but if you are interested in, I'm happy to share the reference in the publications. But anyway, this will segment the entire computation down to smaller fraction, and with that, everything will be carried out. So this will fit onto the FPGA. What else we need to do? So not necessarily ABE, but for the case of ABE, there are lots of the flexibility required for each operations. So to accommodate that, instead of having the fixed sequencing controller is not optimum. Instead, we have this kind of a bit higher level the sequencing or processor is required. It's not a fully the flexible CPU or microcontrollers, but still we have this kind of the OP code based implementation we employ for the flexibilities. For the data bus, basically we can have only two types of the three types of functionality: modular multiplier, modular add and subtractor, and pairing operation or second order the extended field multipliers. So the question here again is that if for the case of the this portion, the optimum for the number of pipeline stages is something like this smaller. For the case of pairing, I mentioned 12 in the past, but for this case 13 in some reason is the optimum instead of the smaller pipeline stages. So how we can manage those two different directions? Of course, you can say that, you can use 7-stage pipelines of the higher clock frequency in one domain, and using this one in slower clock domain, and they're communicating asynchronously. That will be one thing, but that makes entire controlling too complicated. So I don't like that. Instead, we would like to stay single clock domain. So for that, we have analyzed which should be the optimal, and come to conclude that some of the idea that filling those portions for the optimal operations. The problem is how many, say, the functional unit we can accommodate. So modular multiplier is relatively big, or pairing of the engines relatively big. But for the case of the modular adder and subtractor, it's relatively small. So we can increase the number of functional units to some extent. So we examine how much the performance improvement we can obtain for each the operations. So for the case of the simple operation, the performance improvement is not so big. But for the case of the extended field operation or pairing operation, the performance improvement is drastic. So with this kind of analysis, we define the number of the modular adders as well. Then come to how we optimize the pipeline alignment. So instead of so if we utilize this one, clock frequencies are degraded, so performance will be degraded. Utilizing this one, this causes a huge data dependencies. So that causes the performance degradation for simple operations. So instead of just having the vacancies, because the AB or the functional encryption, there are a bunch of data existing. So we can somehow interleaving the sets of data and the operations. So with that, utilizing the different set of data, filling the pipelines, we could come to filling most of the pipeline portion to realize efficient computations. Of course, at the end, the latency for for the single operation is extended a little bit, but still that is very efficient directions. So, of course, there could be some other optimal possibility, so that the not sacrificing the latency. But anyway, with this kind of the consideration over the higher level of the algorithm, we could optimize the data bus much better than just optimizing the pairing or elliptic curve operation. So this is the overall result for such kind of the interleaving technique. So as expected, some of them result in almost doubling the performance. Of course, some of them the performance improvement is not so large, but this is what we obtain for each the functional unit. So basically, with that we could realize higher performance improvement for each operations. Then what will happen for entire AB operations? So if comparing with CPU, this is still the not tightly connected in the accelerator, but we communicate CPU controlling through the PCI Express. So that causes the performance degradation to some extent, but still we could see the performance improvement by 3 times for this case, or up to 10 times for some of the cases. So of course, if we integrate the CPU and tightly coupled with the accelerator, that kind of the communication overhead may be well minimized, so that the performance improvement could be much higher. Of course, for that case, because CPU is very fast, utilizing very fast clock frequency, so that kind of difference also matters. So we need to utilize advanced process for the further performance improvement. So now we are seeking ASIC implementation, including CPU, tightly coupled with accelerators. But for this case, we are utilizing full word size data bus. So we swap the data bus completely from the FPGA to ASIC. So of course, we want to make the modification as minimum, but still that takes quite the effort for doing that. But with that, even utilizing 28 nano process, the performance, the improvement will be much higher than the FPGA, about few times. So that means the comparing with CPUs, I think the more than the 50 times improved performance improvement will be possible. So that is what we are expecting, and we are now implementing that. So taking last 10 minutes, I'd like to introduce the what we are doing for Agile-X project. So sorry, this is a bit busy chart, but we want to increase the number of designers. So maybe most of you are designers or partially designers. So you are really tolerant or hardworking people. So, but most of the cases, if comparing hardware with software people well, are not so tolerable. So they don't want to wait for seconds. They just press compile and want to obtain the results. So, but on the other side, although these days many people are utilizing GPU or some other special devices, but if you want to fully obtain such kind of the devices, then you have to know the hardware itself. So the programming should be much complicated. So in such sense, if we can realize very short turnaround time the chip design with chip fabrication, maybe software people also can come to hardware design or come to the loop of software development. That is idea. And of course, on top of that, if you know how you write the Python code for AIs, how many lines do you write? Maybe 10, 20, or something. Because there are a bunch of the libraries existing. So most of the basic fundamental thing can be done by those libraries. Only few critical idea for you will be described by yourself. On the other side, for the case of chip design, how many lines of variable code are you writing? Maybe most. Although you are getting help from LLM for some portions, still you cannot rely 100% onto the other RTLs. What's the difference between those tools? We need to seriously think of such kind of situation. So with that, of course, higher level synthesis should be one thing, but at the same, or maybe LLM should be one thing these days. But design to use, intensive design use should be very important, or library should be very important. So with that, maybe we can decrease the amount of the hardware description by yourself or by the designer will be minimized. Of course, at the end, if you implement onto the FPGA, quick turnaround time, the implementation will be possible. But as I mentioned, sometimes FPGA and the ASIC are quite different. So to cope with that, the ASIC type implementation would also be expected. how we can realize that to minimize the fabrication? Because if you send your data to TSMC, at least you will require 2 months to 3 months for the chip fabricated. So instead, if you can do only 1 or 2 metal layers by yourself and all the others could be done previously, so just like a gate array or something, that could be the helpful to minimize the fabrication, the cost as well as the time. How we can realize that? Fortunately, we have the equipment, so-called minimum fab, utilizing 0.5-inch wafers. So this is 8-inch wafers, and these samples are the extracted 0.5-inch wafers. So within 0.5-inch wafer, we put gate array. But at the same time, we put this kind of the RISC-V-based the SoCs inside, so that this could be regarded as sort of the Arduino with hardware accelerators. Arduino, you usually program the device, but for this case, you program the hardware or transistors. So this is the basic idea, and this is the wafer that having the metal on top. So you cannot see anything, but below the top metal, we have this kind of the structures existing. And what is minimal fab? So maybe these are minimal fab. Sorry, written in Japanese, but the minimal fab equipment. And chips are inside, because it is very small, 0.5-inch wafers. So every process can be automatically done just like this. So the coding is done just like this. And okay, next step should be the maskless exposure by the laser lighting. So that can be done automatically. And then developing the exposed the wafers or chemicals, just like this. And the metal portion will be etched by the plasma etchers. So for the case, if you just want to utilize the one metal layers programming, that's it for the entire process. So it can be done only in 30 minutes. If you want to realize the 2 metal layers, unfortunately this cannot realize the planar process. So 2 metal layer will be the best optimum. But still, we can put the insulator on top of it. We can put the additional metal, and then we can do the metal etching as well. So at the end, even within 2 hours, you can realize the chip, your chip. So that is what we are expecting. Or we have already realized this one. So now we are somehow how we can utilize the platform. Now the chip have been already completed. So of course you have a question how you can realize the 0.5-inch wafers. Of course, there are the company that can sell the 0.5-inch wafers, but for our case, we have the already fabricated the structure under below. So we have to extract the exact position. So because of that, we realize this kind of laser cutting machines, and with this, we generate 0.5-inch wafers from the 8-inch wafers. By the way, 8-inch wafer is coming from TSMC. So we have this kind of design environment. This is manual design, but we also having the automated design or automated logic synthesis and present route design possible. And we can do the design verification by extracting the simulation and so on and so forth. And then after maybe 30 minutes, we can realize this kind of chip. And of course, we can attach the oscilloscope for the measurement. But at the same time, because we have the RISC-V processor on chip, so we can just connecting USB to JTAG to the RISC-V processor on chip to measure the other functionality. So this is what we have been implemented, and these are the chips that is done by both undergraduate and graduate school students during the experimental courses. So most of them are correctly operating. So this is what we have been doing. So although the minimal feature size for metal wiring, currently we are using, I think, 5 micron by 5 micron, 5 micron line and 5 micron pitches. We are now experimentally using 1 micron line space. It is almost ready. So with that, if utilizing 5 micron, the number of gate size we can implement is something like hundreds. But if we employ 1 micron by 1 micron, number of gate available becomes almost 10,000. So if you have a 10,000 gate, I think the many things becomes possible. Unfortunately, not elliptic curve-based crypto accelerators, but still, some of the small fraction of the data path could be possible. So that is what we are targeting right now. And also, the important thing is with this, the platform, we can say we try as many as possible. For if you are submitting your data to TSMC, you will be scored by your professor if you want to. You are saying you want to retry because of the cost, of course, because of the time and so on and so forth. But for this case, you can retry. If you find the many improvement, you can do that frequently. So of course, I'm not quite sure whether you agree or not, but for the case of software, they are doing such kind of the gradual improvement. Maybe by compile, they are doing some improvement. And at the end, maybe after 1 year, how many times they can improve? Maybe 100 times? If the improvement of each time is only small fraction, like a few percent, if you continuously doing 100 times, improvement will be drastic. So that is what we are expecting. So even you can do 1% or 2% performance improvement. If you can try for many times, at the end you will obtain, say, the 100x of performance improvement. That is my dream or my expectation doing this kind of things. So, of course, we need to try, but that kind of thing could be open the new vista for chip design. Currently, you have to seriously work for correct operation with certain target performance, taking quite a long time, maybe 1 year for design or something. But with this kind of environment, maybe you can try gradually. That makes much easier situation for design, and hoping that would enable many people to come into design. So that is what we're doing. So in conclusion, of course, I have demonstrated the realizing functionality. So to realize functionality, we need to do step by step. But at the end, we need to optimize the entire data path. So that is the important messages. On the other side, the short-term time chip design and fabrication platform will be not necessarily democratizing, but also enabling trying many kinds of trials to further improving your chip performance, and also increasing the number of designers. So that is all I have today, and thank you very much for your kind attention. And if you have any questions, I'm very happy to answer.
Professor, for sharing your insights. We can take some questions.
My question is that when we are talking about that interleaved operations with the Q2 operations and all those things to improve the utilization efficiency,
Which one again?
I think it was around 48.
48. This one? Yes.
So are these blue operations and the green operations, are they independent? Are they coming from two different sources?
Yes. Basically, the just like the searching operation or some others, the AB, they require the many entities for the completing the entire AB operations. So with that, we can have many sequences of the data sets coming. At the beginning, we expect we can do sequentially to reduce the amount of memories. But if you can do this kind of interleaving for two data sets, that helps quite a lot. Of course, I'm not quite sure whether we should increase that one to 3 or 4. We are still seeking, but we need to consider about amount of memory as well as the performance improvement. But yes, so those are the completely independent data. So that's the reason we can do that freely. So that is the fact we are doing. And that is because functionality is one level up to the fundamental operation.
Sure. Thank you for the data.
For the Agile-X project, what entities are we are fabricating on the lower levels?
Okay, so for you are talking about this gate array portion.
Yeah.
So at this moment, we put the C of gate here. So it's just a pair of PMOS and NMOS. That's it. And with that, using the top metal layers, we form the standard cells. And then, of course, using the standard cells and press and load for the between the cells, we realize the functionality. So, of course, there are many other possibilities. Of course, we put sort of functionality in the bottom side, like a flip-flop or some other fundamental gates. That will be somehow the result in efficient the result, but on the other side, you might waste the number of gates. So that's a trade-off. So now, actually, we are thinking of what kind of thing will be the best optimal utilizing this kind of the platform. So something like just like an AI or the neurons. Such kind of coarse-grained functionality might be one possibility for this kind of platform. But still, we are investigating what should be the best. And of course, one of which could be general purpose crypto, the processing element as the fundamental function. Then we can just connect some of them to realize, say, functionality or some other stuff. So that is the next step for the platform portion.
Thank you, sir.
So maybe continuing on this, so how many total metal layers are you having?
For this case, it essentially gives us the 5 metal layers. And the topmost, meaning 5 metal 5, we utilize as a metal 1 of our Agile-X process. And we can add one more metal layer by ourselves. So in total, we can utilize 6. But I should say that the most of the metal layer from the metal 2 to 4 is utilized for these the peripheries, RISC-V memories, AD converters, and some other peripheries like the UART and so on and so forth. And for gateway portion, it's just a plug to the top metals.
So the minimal fab is adding just one metal layer.
Could add one metal layer. I haven't said detail, but we have a metal sputter here, so we can put metal layers. But because we cannot do the CMP process. So because of that, if we want to put 2 additional metal layers, it might be some issues. So that's the reason we, at this moment, limit up to 2 metal layers.
Also, you were mentioning that you want to motivate more people to do trials on this design. So suppose this metal layer formed from the minimal fab has some mistakes. So can you remove it and do one more round on the same die?
Instead of removing, you can try another wafer. Yeah, so that kind of the easiness would help without any pressures.
Thank you, Professor. Thank you again.